In this lecture, I will be talking about application of zero-shot learning for relation extraction, and in particular this interesting article in 2022. The idea is that zero-shot relation extraction aims to predict target relations that cannot be observed during training. So during training, we just work on seen data, and in test data, we are working on unseen data that hasn't been trained. They haven't been trained in the training phase. So our aim is to predict the target relations that cannot be observed during training. While most previous studies have focused on fully supervised relation extraction and achieved considerably high performance, less effort has been made toward zero-shot relation extraction. This study proposes a new model incorporating discriminative embedding learning for both sentences and semantic relations. In addition, a self-adaptive comparator network is used to judge whether the relationship between a sentence and a relation is consistent. Discriminative learning helps models to better distinguish relations, especially on similar relations. So their study focused on this aspect and demonstrates its significance for improving zero-shot relation extraction. Specifically, we propose a new model that incorporates discriminative embedding learning for both sentences and semantic relations, which is inspired by, I have a playlist for this contrastive learning as well as Siamese networks and contrastive network as well. They are mostly in computer vision, but you can also use it for natural language processing. So what is the task definition? We have seen data and unseen relation labels. They are disjoint, so there is no intersection between your seen data and unseen data. So given a training set with n sub s samples, the I sample consists of the input sentence x sub I and the entities and the description of the corresponding seen relations could be seen like this. So you have some entities and you have the relation label. But not only that, you also have some description. You have also some description. So the sentence encoder, we add 4 entity marker tokens. This is for start of entity 1. This is the end of entity 1. This is the start of entity 2. And this is the end of entity 2. So we use this pre-trained BERT encoder, and then we obtain the vector representing the relation between the two entities by concatenating the two vectors of start token, the one that corresponds to E1 and E2. Because each relation, that means that you have two entities. So for relation encoder, most relations are well defined and their descriptions are available from, for example, Wikidata. So for each relation, for example, founded by is a relation. We input its description into the BERT encoder and obtain the representation vector by using mean pooling, because if you give it to BERT, then you have a representation. But you have lots of vectors, so it's better to do some pooling mechanism to reduce it into just one vector, because at the end of this algorithm, you need to just compare it with just one vector, not a couple of a sequence of vectors. So here you present n sentences assume you're working on a batch, you have n sentences, you just do what you do for scene relation classifier, you know how to do it. But now there is also provided some descriptions for your relations, even unseen relations. At least you have the description, although you don't have a label, but you have description. So why not using this information and then concatenate this and then giving to this in comparator to say that, for example, this sentence goes to that one. What is the probability? Is it match or not? And so to boost the learning of discriminative embeddings for sentences and relations, we consider three main goals in training: discriminative sentence embeddings, discriminative relation embeddings, and effective comparator network. So for discriminative sentence embeddings, we know how to do it. We just use this softmax and then multi-class relation classifier, and this is the loss of that. And then the discriminative power characterizes feature in both separable interclass and compact intraclass variation. So the similarity distance between two sentences is here, and we can now formulate the loss. We want to increase the similarity between two sentences. And we have positive pair, negative pair as usual, so we want to avoid negative things, negative pairs, and so we try to minimize their factor. So here we have softmax. This is the loss of softmax, and here this is sentence to sentence. The loss that we say it ensures interrelation compactness. And finally, we have for relation embeddings the same thing for relations, because we have a total of Q pairs, K relations, then what remains? K minus 1. So we multiply K and K minus 1. But many of them are redundant, so just multiply it and divide it by 2. So this is how they created. And finally, this comparator network is the thing that does all of these relation classification for unseen relations. Because you have a set of negative samples, you have a set of positive samples, and you want to reduce those negative ones. And finally, the total loss is sentence, relation, and this one, the comparator. But in the testing stage, we conduct zero-shot relation by comparing the similarity score of a given sentence with all the unseen semantic relation representations. So we classify the sentences as sub I to the unseen relation that has largest similarity score among relations. So the probability of that S sub I is like this.